Well, it's a real pleasure to introduce Eric Howeler, an architect, designer, and educator, a triple threat. He's currently associate professor in architecture at the Harvard Graduate School of Design, and no pressure, I'm sure he is busy inspiring several Mount Holyoke alumni who are in that program. He is the co-founder and principal of the award-winning design firm of Howeler and Yun Architecture that has realized projects in the United States and China on both sides of the Pacific. He's also a very industrious author and has co-authored The Expanded Practice, 1,001 Skyscrapers, and Public Works Unsolicited Projects for the Big Dig, all with Mi-Jen Yoon, and has also written the work Skyscraper Vertical Now. So it's a pleasure to welcome Eric here, who will be talking about verify in field. Eric, thank you.
Thanks, Michael. I'm going to try to share my screen, see if I can do this properly. Try to oops, sharing the wrong screen here. On 1 second, I'll try that again. You can see my messy desktop.
No, we can just see your video, but in a second. Yeah, now we can see it.
Okay, so saving my messy desktop. And how about now? Can you see my, is it in presenter mode? Or can you see my notes, or can you see the
No, we can see your notes.
the image? Okay, so here we are. That's my title page. Thank you, everyone, for the invitation. I've enjoyed these talks coming from all different sides. I'm delighted to follow Mark and Alejandro, and delighted to meet Chris and all of you. My talk's called Verifying Field, which I hope sort of touches on many of these points that have already been raised by some of the speakers and were sort of provocatively framed by Pari and the group. So Verifying Field, or VIF, is a notational convention employed in architectural drawings, indicating that the information on the drawing is incomplete and further field measurement and verification is necessary. The note reveals a gap between design intent and built reality. The term also acknowledges our disciplinary investments in the instruments of design, drawings, models, and prototypes that are the discipline's means for operating on the world at a distance. Verification in this case may refer to a field dimension, alignment, or survey point. It may also refer to the process of feedback, where information and expertise is fed back into the design process in ways that inflect the original design. Or, as I hope to show in this presentation, verification may include a number of other factors having to do with political and/or environmental contexts for design. The field as construction site is understood to be outside the scope of the architect. It is the space of contingencies, externalities, and uncertainties, the intolerance that Mark and others have referred to. While VIF may be understood as a disclaimer, architect's fine print, the notation speaks volumes about the disciplines and the profession's culture of risk, the role of representation, and our agency to act on the physical world. Verifying field cleaves apart the realms of conception from construction, model from building, representation from execution, and architect from builder. Beyond a strict delineation of scope, risk, and responsibility, the separation of representation from building is significant for how we conceptualize the disciplinary practices, especially as these evolve with new technologies. We understood from Robin Evans and others, drawings precede buildings, yet contemporary drawings are not drawings at all, but vectors, information, often assembled as digital models, blocks, and data. The contemporary design workflows are altering the assumed sequence and priority and precedence, introducing new instrumentality to drawings/models as fabrication tools and challenging an inherited assumption about the hierarchy between buildings and models. At the same time, the status of the physical building and its materials are being reassessed. Post-occupancy evaluations, life cycle analysis, and material obsolescence also question the notion of the building as the endpoint for design, and the completed building often initiates another series of models that have to do with monitoring user behavior and energy consumption. While verifying field is the most mundane level, addresses the physical and contingent conditions of construction, my use of the term to frame contemporary design processes examines the term as a kind of modality, one that develops the means for more agency, responsibility, and engagement. This telling shop drawing shows an interface between a precast panel and a window wall system. The dotted lines represent a combination of facade erection tolerance, precast fabrication tolerance, precast erection tolerance. Not shown in the diagram are deflection tolerances, concrete creep, column shortening, and live load deflections. Adding these factors together, the joint could be either 1 1/4 or 3/8 inch wide. The acceptable range of joint width varies from 5/8 of an inch, all absorbed by the compressible backer rod and caulk. The multiple possible acceptable geometries of fabrication and erection point to the unknowability of the actual conditions in the field and the necessity for techniques for tolerance. Today, I want to show 3 projects through the lens of verification and field conditions. In each case, the project involves questions of fabrication and precision, erection and tolerance, and necessitates a vigorous back and forth between model and material, shop and field. The 3 projects also define field in different ways, having to do with the field of construction, the field of public engagement, and the field of environmental thinking. So the Collier Memorial was built in response to the killing of MIT police officer Sean Collier, who was killed by the Tsarnaev brothers after the Boston Marathon bombing in 2013. In the following days, an informal memorial sprung up on MIT's campus as people sought a form of expression for their grief. In response to the marathon bombings, a campaign emerged to remain strong. Boston strong, MIT strong, Collier strong. Strength, it seemed, was the response for domestic terror. We asked ourselves if strength and structure might offer clues about the appropriate response to the memorial design. Our design concept was to create a figure that would convey a conspicuous absence. We chose to carve a figure-like boulder out of the 5-fingered form. The visitor would be confronted by the missing figure whose contours were inscribed in the interface between the figure missing and the standing walls. Additionally, we proposed to make the figure into an arch or vault, constructed of solid stone blocks. The principle of the arch is that all blocks transfer load to adjacent blocks until they meet the ground. The challenge of building an arch with today's construction techniques introduced some complexity. No one had built a full compression arch in a long time. Discussions between our engineers and contractor worked through questions of sequence and constructability. Computer modeling by our structural engineers and masonry consultants resulted in different solutions based on different assumptions. They did, however, agree that the shallowness of the arch meant that the structure was very deflection sensitive. The stone blocks would need to fit together with a high degree of precision in order to stand. Small horizontal displacements would mean significant vertical displacements. That means it would fall. The various models employed in the conception and construction of the Collier Memorial exemplify contemporary digital workflows relative to modeling, simulation, and verification. The procurement of stone required blocks larger than industry standard blocks that were optimized for slabbing kitchen counters. Searching for blocks suitable for the keystone required special procurement at the quarry and several rounds of adjustments of the block geometry to fit within the bounding box of what was quarryable and what was transportable. Verifying blocks to ensure that the expected block geometries would fit within the overall quarry blocks. We also began discussions about fabrication equipment, capabilities, and tolerances. The fabrication process involved translating the geometrical used by the fabricator to carve the finished blocks. This involved a series of different tools, including CNC saws, multiple axis industrial robots, and the use of our 3D model of fabrication, which introduced questions of responsibility, ability, quality control. In a traditional process, the architect's drawings are intended only. The fabricator would typically produce their own shop drawings for fabrication, and the review of the shop drawings would result in the quality control. By treating the architect's files as fabrication files, the project required rethinking the whole QA/QC process. Shop tickets for specific blocks were fabricated based on digital files, and then each block was subsequently dimensionally checked in the shop before shipping. We tend to have a great degree of confidence in the digital tools, perhaps overconfidence. As Francesca Hughes has pointed out in her book, The Architecture of Error, our overconfidence in the digital relegates exceptions to the category of error. With every pass of the digital saw, the stone is carved away. We have a specific set of X, Y, and Z coordinates that tell us the precise dimensions of the stone, where the stone is supposed to begin and end. While we were fabricating the memorial, the owner of the company, Cora Stone, Jim Durham, asked us, "Where do you think the interface between the saw and the stone is?" And he asked, "How do you know where the stone is? How do you know?" Because the saw is wearing at the same or a different rate than the stone. This question about the precise coordinates of the stone geometry is complicated because the stone and the saw are both wearing, just at different rates. The diamond tip saw is also subject to the brute processes of grinding and wearing. The stubborn materiality of the granite registers against the diameter of the saw, causing both to yield. This was eventually addressed by performing a frequent recalibration of the saw to verify its actual dimension and then updating the toolpath appropriately. But this sort of question of the saw diminishing really sort of threw us for a loop, thinking that certainly a digital fabrication process would know exactly where that boundary was. The fact that that boundary was sort of constantly shifting by millimeters as the saw blade was diminishing in size was kind of mind-blowing. During the process, we developed 32 unique blocks, each of them fitting together with this tremendous precision. We managed the blocks through these tables, managing the weight and the dimensions and the shipping. And then when they come together on site, they sit on a grade beam. So the thrust of the arch is being picked up by the sort of tension in the grade beam. As the blocks arrived on site, they were being checked. Each block was checked on the truck before it actually got off the truck. And this block shows some of the beautiful veining that we have. We picked a stone that has a charcoal background and a white kind of feathery vein. We thought that by watching and following the vein around the block, we sort of appreciate its three-dimensionality. The traditional arches are built with scaffolding and falsework, sequencing assembly from the buttress to the center, with the keystone completing the arch. The precision required for the stones at the Collier Memorial necessitated a reverse process, starting with the keystone and working our way out so that tolerance was driven outward from center to periphery. The 5-sided keystone was set first, and the 5 adjacent ring stones were fitted to the keystone. And this is because the keystone had a step profile. So although it has 5 sides, in plan, it has 15 faces that needed to align perfectly. The faces of the keystone are perpendicular to the thrust vectors of the buttresses. So you can read in a way that sort of keystone geometry is related to the perpendiculars of these arches and those vectors. Each interface between keystone and ring stones consists of 3 faces. I mentioned that. 15 faces come together on this one keystone. The erection sequence of working from inside out reorders a traditional process of working towards the keystone. Because the blocks were transferring loads from block to block, the precise alignment of the stone-to-stone interfaces is critical. This drawing shows the interfaces between blocks where the load is being transferred from block to block. From the outside, we read these as joints. You see that line between 2 pieces of stone. But really, we're talking about interfaces of stone perfectly parallel to the adjacent stone to ensure the transfer of loads through those interfaces. The joint between the stones is only a 1/4 inch wide, which does not allow a lot of room for error, either fabrication or erection tolerance. A precise fit is the only way that the arch actually works without the risk of the joint stones opening up. During the construction process, a team of researchers at MIT applied strain gauges to the joints to measure displacement. These strain gauges effectively turn the built structure into another kind of model, a verification model. The last model is the built structure itself. It serves as a means to compare the real against the analytical, and a means of validating the design after the fact. In the process of lowering the scaffold, the keystone supports were lowered first. The scales installed under the scaffold allowed MIT researchers to visualize the load transfer from the keystone to the ringstones and eventually to the buttresses. It's impossible to see force traveling through material, but it is possible to measure the shifting of load from center to perimeter during the scaffold removal process. And these are the MIT researchers which were trying to observe the kind of shifting of weight and what they called arching action. The removal of scaffold revealed the vaulted figure of the void. So this is the first time we saw the kind of void kind of exposed without the scaffold. And once completed, we were able to appreciate the contrast between the smooth finish of the interior and the rough texture of the exterior faces. The concave figure of the conspicuous absence is distinctly legible within the memorial, and the low angle of the arch seems to span effortlessly from buttress to buttress. The memorial, when seen from above, looks like an open hand or a star shape. It occupies a gateway condition to the MIT campus. On the left is a fire lane. This serves all the buildings on the MIT campus. And the only load condition that would cause this memorial to fail was a direct hit from a fire truck. So in order to avoid that, we placed all these blocks in the way. These are kind of bollards to protect the memorial against the impact from a fire truck. A few years later, a driver on Vassar Street lost control of his car, somehow managed to avoid all the bollards and hit the buttress wall. Fortunately, it was not a fire truck, but a minivan, and the memorial survived unscathed. So the completed memorial illustrates a contemporary design workflow where computational tools for design, analysis, and fabrication are combined in an expanded document. The digital model that combines the instruments of service with the toolpaths for fabrication and a means of post-occupancy verification. The measurement, the process of procurement, fabrication, installation, and erection are incorporated into these documents, creating feedback loops for verification, control, and assurance. So that's project number one. Beyond the scale of building and building site, how else might we find the terms verification and field to offer insights into design where the cultural and social context are the scope and motivation for design? The memorial to enslaved laborers at UVA involved the precise fabrication and installation of massive blocks of stone, rendering it a technical artifact. Yet its impact is felt on a different register, engaging difficult institutional histories and larger questions of contemporary racism, rendering it a cultural and political artifact as well. The University of Virginia is one of Thomas Jefferson's great achievements, and in some senses, embodies the ideals associated with American higher education as an academical village and American democracy. This statue of Jefferson installed on campus depicts Jefferson in the process of surveying the campus. Equipped with a sextant and a topographical survey, Jefferson the surveyor, the planner, and the architect is depicted as a great visionary, peering into the future to transform map into territory through the execution of his vision for the academical village. The UVA grounds depicted here in this 1830 engraving show the ideal campus as designed by Jefferson, 10 classically inspired pavilions, each 2 stories tall, and a rotunda and a colonnade frame the rotunda. Yet the ideal society that Jefferson envisioned relied on the forced labor of African slaves. The image on the lower left corner reveals the basic structure of slavery on which Jefferson's plan relied. This blow-up of the engraving shows an African woman caring for a white child. The forced labor of slavery is hiding in plain sight, even within Jefferson's utopian archetype. A cross-section through the lawn reveals the 2-story pavilions are in fact not 2 stories, but 3. Jefferson's work as land surveyor placed the lawn at the ridge of a hill upon which the grounds were built, allowing the rotunda to occupy the highest point, and allowing the pavilions to have walkout basements. The lower level of the pavilion buildings house spaces for the labor of the enslaved. The spaces behind the pavilions, enclosed by the famous serpentine walls, were workyards where enslaved labored to chop wood, haul water, and slaughter animals. The institution of slavery is built into the foundations of the university, literally. Jefferson understood slavery to be abhorrent and therefore employed architecture and the architectural section to conceal it. In the process of designing the UVA memorial, we assembled a team of collaborators. Our team included historian and architect Mabel Wilson, community engagement specialist and UVA professor Frank Dukes, landscape architect Greg Bleem, and visual artist Eto Otetigbe. Before the design team designed anything, we first designed a process of community engagement, spending 6 months meeting and listening to stakeholders from the university as well as to community members, many of whom were descended from the slaves that worked on the grounds. Meeting in churches and high school gyms, community centers, and classrooms, we heard a lot about the generational distrust of the university from members of the community. The grounds were referred to as the plantation. We also heard that for the memorial to be legitimate, it would need to tell an unvarnished truth about the past. There was a sense that the history of slavery at the university had been covered up, and the memorial's job was to acknowledge that and to daylight that history. Studying the various proposals and multiple sites, we turned to the idea that the memorial should be a place of gathering, allowing people to gather in the present to reflect upon the past. Unlike many monuments that stand as an object in space, the memorial would be a space or a clearing intended to be occupied and completed by people. We also learned of an African dance called the ring shout, where performers sing and dance in a clockwise circle. With these principles in mind, we proposed a clearing and a circular figure as a place of gathering and remembrance. The geometry of the memorial enters into dialogue with Jefferson's rotunda, where the half sphere of the rotunda's dome is complemented by a bow-like form of the memorial. The memorial is actually made up of 2 cones intersecting slightly off axis and resulting in a tilted figure that emerges from the terrain as the center ring cuts into the ground. The memorial consists of concentric rings. The outer ring is heavily textured and references the pain and bondage of slavery. The inner ring lists the names of the enslaved. The water feature contains a timeline of the history of slavery at the university, and the middle is a pristine gathering area planted with grass. A cross-section through the high point of the memorial shows the geometry of the landform with the inclined walls and the circular path, the timeline, and the bench. A full-scale mock-up in our studio shows the geometry of the memorial relative to the body. Standing with your foot at the base of the slope of the inside wall connects your foot to your outstretched arm, thereby inscribing the body in the geometry of the memorial. A partial mock-up with the stone panels in the stone yard to verify the kind of precise geometry of the cone. The inner surface of the memorial contains the names of the enslaved. Based on the records, historians have estimated that approximately 4,000 enslaved individuals labored on UVA's grounds between 1817 and 1865. But the records are sparse. Slaves were understood as property, so the records contain logs of transactions that often lack basic information like names. Of the 4,000 enslaved, we have 963 individual records and only 652 partial names and only 6 full names. So in translating the names of the records to the wall, we opted to inscribe 4,000 marks to act as placeholders. These underscores are kind of reserved places for the 4,000, in a way, some of them nameless individuals. They are placeholders. They represent the unknown individual. The names are known are added to the underscores, like Isaiah and Farmer and Henry. These represent the names that are recorded, or their tasks and their crafts, or their kinship. The absence of information, the missing names, is almost as powerful as the names themselves. This week we learned that there are 3 new names that were discovered. So we're going to add those names to the memorial. And in a way, the kind of open-endedness of the underscore is in a way a placeholder for adding those future names. So the hope is that we can add names in the future as scholarship uncovers new names, or as DNA research identifies new names of enslaved individuals. This image shows the memorial after an afternoon thunderstorm, where the water collects in the cuts and spills out like tears. The outer surface of the memorial is highly textured, evoking the rough stone of a cleft gravestone or the scar tissue as shown in this photograph on the left. The image in the middle is Isabella Gibbons, a freed slave and one of the few existing photographs of an existing enslaved person on UVA's grounds. We collaborated with Eto Otetigbe, who's a visual artist. He worked to develop the pattern that incorporated the textures and traces of labor of carving stone. Here, Eto is bush hammering a granite stone in the shop. And these are digital models of a kind of scalloping pattern that we developed by looking at the cleft stone finishes that Eto was interested in. And we combine the cleft finishes with the kind of parallel patterns that evoke the qualities of drill marks from a quarry. So scalloped and quarry marked, that's how we arrived at the pattern here. Eto's previous work includes this piece called Becoming Visible, where he photographed himself in a hoodie, a reference to Trayvon Martin, and inscribed his portrait in stone through a series of parallel lines. Eto proposed the same treatment for Isabella Gibbons' eyes, cropping the image around her eyes. And this image shows a mock-up that we did in the shop using that technique of the kind of converting a raster file to a series of cuts. You can see the cuts and the grooves are varying widths and varying depths, and that translates a kind of image, this raster image, into a series of vector lines or tool paths that are ultimately sort of carved on the stone. These are images of the prototypes as they're sort of laid out in the stone yard, and you can almost see the image of Isabella Gibbons' eyes here in the middle of this center block. And as installed, these panels, the legibility of the image, you can just make out the two eyes sort of looking from this colossal image of Isabella Gibbons. The legibility of the image is highly dependent on the contrasting light as it falls on the grooves. In some cases, it's barely detectable. In that sense, the image and the representation of the enslaved is quite nuanced. Sometimes it's visible, at others it's not. This nuance was embedded in the technique of carving the stone and translating the photographic image into the contours of the stone. While the Collier Memorial depends on precision for its structural integrity, the UVA Memorial depends on precision for its legibility. Carving the raster grooves into the stone was done with this industrial robot. Now, the selection process for the stone fabricator, we asked 3 pre-qualified fabricators to carve a stone sample, about 3 foot by 3 foot. We provided the 3D model, they produced the tool paths. After the sample panels were produced, we hired a third party to perform a 3D scan and compare the scan to the original file. This fabricator A had a number of deviations from the third model, as much as 2/100ths of an inch, these kind of red zones. Fabricator B had fewer deviations in the 3D model, and so we awarded the job to fabricator B. As we think about precision and contemporary workflows, it requires us to rethink traditional processes of QA and QC, the checks and balances of fabrication and construction. The promise of digital fabrication does not ensure an outcome, as what looks acceptable to the naked eye may conceal deviations that are the result of a translation from model to toolpath. Now, shifting from fabrication tolerance to erection tolerance, here we see the setting of the first stone panels in situ. Again, everything is built up in the air upon shims to be backfilled with grout after the geometry is confirmed. The challenge of architecture is of part-to-whole relations. Even as the architectural form is conceived as a monolithic ring, the implementation in the field is of multiple parts coming together to form that singular line. The memorial relies on that ridge line to create the new horizon within which the contemplative space of the memorial is constituted. This construction photo shows the incredible continuity of that ridge line. Even though you see that the blocks are different colors, we see the continuity of that horizon as it sort of delimits the space of the interior of the memorial. It looks like something that flickered across our screens for months leading up to the construction. The alignment of the individual parts is additive, yet the geometrical operation that produced it is, the alignment of the individual pieces is additive. Most architecture is additive, yet the geometrical operation that produced it is subtractive. The Rhino operation is a Boolean difference, subtracting one geometry from the other. Yet, as I said, all architecture is made of parts, and the joint at the ridge line shows how these two panels come together, the smooth inner panels and the rough exterior panels. And this detail shows the quirk miter where they come together, where the knife edge has been blunted to avoid breakage in the field. The gap between the two is filled with backer rod and silicone caulk. Another look at the continuous ridgeline, appearing eerily familiar, like something we saw on our computers just a few weeks before. Like you're in the presence of something that has escaped the digital and is present in the real world. How is the stone aligned to create this continuity? A number of hydraulic jacks lift the stone into position while a digital surveyor verifies the points in space confirmed with the digital model. The effect is the appearance of a monolith. even though we know it's made up of many parts perfectly aligned. Here in the center, we see a 1/4-inch joint located at the center of the groove. So like the color memorial, the UVA memorial relies on the interfaces between discrete parts. In this case, the faces are not transferring forces, but their alignments are essential to the monolithic reading and the legibility of the colossal eyes. Here we see some of the stone panels coming together. Here it's almost complete. And here's the completed memorial. Seen from the other side at the entrance. And the memorial does allow the viewer to measure their body against its geometries. The water feature contains a timeline of events documenting the history of slavery at the university. The views from the exterior highlight the landform-like qualities, the contrast, the smooth interior, and the rough exterior. And recall the traces of the digital, casting shadows in the real. The construction of the UVA memorial involved high degrees of precision and processes of testing, measuring, validating, and verifying. It also unearthed painful histories. But the completed memorial has been embraced by many in the community, and the UVA has acknowledged that the impact of the memorial is the rebuilding of a trust with the community. The field of work, in this case, is bound up in the history of the processes of recognition and reconciliation. So I'm going to shift to the last project here. As we expand our understanding of design to include the broader context in which we're working, the labor that has gone into their assembly and communities that they impact, and the environment that they become a part of, it is useful to think about building as noun as well as verb. The process of building involves flows of material and labor, energy and waste. The building itself, the noun, is just a moment in a much larger process. Kielmo has described the physical building as an isolated object instance within a much larger network of linkages, processes, and flows of material and labor. The last project I'm going to show is an inhabitable sculpture located in Spokane, Washington, on the site of the former 1974 World's Fair Expo. In this case, the structure is conceived of as an instrument for looking, for surveying the site. The diagonal cut through the structure is surveying the site. The diagonal cut through the sculpture creates a sightline relationship across the landscape to another sculpture. You can just see another sculpture through this aperture right here. The figure of the surveyor sighting across the landscape became part of the concept for this project. The site itself is quite dramatic, with gorges and waterfalls that historically were part of the Spokane tribe's hunting and fishing grounds, and eventually became part of the development of Spokane's mill and hydroelectric power industries. Our initial studies showed alignments across the site's topography and the potential for multiple pavilions to be sited relative to each other. The history of logging in the Pacific Northwest is also something we wanted to call attention to. The use of wood as a basic raw material that was associated with the place. Evaluating the environmental aspects of building today requires that we take into account energy performance as well as material embodied energy footprints. And as architects, the agency in specifying material or a system is actually one of the most significant decisions we make in the design of buildings. By specifying wood as a construction material and substituting for steel and concrete, we're choosing to avoid energy expenditures of high energy practices of extraction and processing. Building with renewable materials such as mass timber has the benefits including carbon sequestration and impacts on land uses and forestry practices. As part of our research into mass timber as a building system, we proposed Stepwell as a public art installation in Spokane with a stacked mass timber structure. Understood as a device for looking, the Stepwell project gestures beyond itself with the diagonal sightline that bisects the plan, and a lookout platform at both ends of the structure. The exterior is sloped to accentuate its cantilevered form. The interior profile is terraced for seating. The non-parallel faces of the interior and exterior suggest a use of material as a volume, no longer composed of beams and planes. The mass timber industry is evolving to scale up beyond the traditional wood workshop and embrace the scale of engineered lumber well beyond the dimensions of wood sources, namely the size of a trunk. Engineered wood takes advantage of glues and composites which reconfigure wood to improve yields and optimize components of varying qualities. However, the mass timber industry is primarily focused on cutting flat sheets and beams, relying on cutting sheets in planar configurations perpendicular to the surface. Yet the multi-axis industrial robot is capable of far more three-dimensional work envelope, which allows it to cut volumetric elements like blocks of stone. For the Stepwell project, we began testing the work envelope of a robotic mill to be truly massive mass timber elements. Rather than substituting conventional building elements with alternative materials, we opted to conceive of a structure that was inherently volumetric and use the mass of the mass timber to implement it. The Stepwell consists of 70 blocks of stacked blue laminated tiers of Alaskan yellow cedar. Components are fabricated in the shop as volumetric blocks and transported to the site and erected in large pieces. Maximizing the size of the blocks reduces the field labor and relies on the precision of a shop fabrication environment. It also limits time on site, and time also translates into error. Optimization involves making repeating blocks that stack to produce a Stepwell geometry. And the erection sequence shows process of assembling large volumetric parts to form the singular whole. It's also symmetrical, by the way, Alejandro. Okay, each species of wood has unique properties, including grain character, pest resistance, weathering characteristics, and expansion due to moisture control. Alaskan yellow cedar was selected in part because of its weathering characteristics. It's expected to weather into a silvery gray. Like all works of architecture, construction involves assembling of discrete parts into a singular whole. How those parts fit together is key, as every joint is an interface of force, alignment, expansion, and contraction. Minimizing joints allows for more control, less field contingency. The structure produces a monolithic interior, scaled to the body and to its ergonomic proportions that has a distinct form on its exterior appearance. By constructing the sculpture out of solid blocks of timber, we sought to create a unique structure, one that recalls the material history of the place, as well as one that speculates on new uses for mass timber products. The volumetric mass of the mass timber form, steps and walls of the Stepwell project suggest monolithic construction, more akin to masonry construction. The blocks of mass timber resemble the corbelling in stone. The volumetric use of mass timber learns from the use of volumetric stone from the Collier Memorial and the UVA Memorial, where the fabrication envelope of the robotic mill is employed to arrive at a solution that is inherently volumetric. Stepwell is understood as a stereotomic mass that produces spatial and structural configurations that are analogous to the vaults and shells rather than frames and skins. The use of mass timber in a truly massive way reveals a new expressive potential for engineered wood, not simply as a substitute for steel and concrete, but as an alternative to previous construction modes of what Elise Iturbe would call carbon modernity. To find alternatives to carbon form requires prototyping new modes of carbon sequestering, rapidly renewable building materials that offer new possibilities. An accounting of the embodied energies projects like Stepwell offers alternative material flows and energy footprints. Thinking through material, its qualities and quantities, procurement and processes allows us to imagine an approach to building with the earth in mind, what Bruno Latour would call an earthly account of building, or an architecture of accountability. So the translation from drawing to building, from concept to construction, is never a linear process. Despite our digital tools and digital fabrication techniques, in construction, there's ample room for friction, gaps for tolerance and deflection, anticipated and unanticipated conditions that require the feedback implicit in the verifying field notation. In each case, field conditions, constraints, motivations, and materials are different, but the strategies for working back and forth across the boundaries of conception and construction, between design intent and means and methods, community and climate, have been instrumental. Strategies for verification, integration, and tolerance become drivers for design, where materials and methods, engagement, and environment impress themselves on the apparent seamlessness of our digital design process. Contemporary use of digital tools, whether 3D modeling or cutting stone with a robotic saw, are all working through media. In our own work, we have shifted from arguing for an expanded field, including media as material, to contemplating the status of material after media. The Cold War quip of trust but verify, attributed to Ronald Reagan in the context of the Cold War détente, contains a fairly direct assertion that truth could be verified. There were or were not missiles in the silos. Writing in 2020, weeks from the election, it seems that the common understanding of a shared reality, a shared understanding of truth, and the articulation of common values seems more and more remote. The paradox is, in the age of post-truth, coincides with the information age, the age of big data, and of peak knowledge. Yet the need for verification for systems of feedback and techniques of translation has never seemed more urgent. Thank you.
Thank you so much, Eric. I believe Michael is going to ask the first question.
Okay. Did I stop sharing my screen?
Yes, please do.
Okay. I'm not sure how.
I stopped it.
There you go. Great. Thank you.
Michael, I think you're muted. Oh, it seems that Michael is, for some reason, not connected. So we'll see. We don't have questions yet, but I'm going to ask you a question. So in terms of process.
I'm back. Okay.
You're back. Okay, go ahead. It's
No,
your question first.
Harry, please go ahead.
No, it's okay. You're the chair of the session. Go ahead.
Okay. I wondered if you could talk about, of course, the Collier Memorial struck me as, they've been building arches a long time. There would be no Gothic architecture without arches. And I wondered if you could talk about the sort of conversation between the size of the blocks and the technology. Was it the existence of a certain kind of foundation of technology that permitted the use of large blocks, or did the size of the block push the existing technology into a new space of fabrication?
Yeah, it's interesting you brought up the Gothic. I mean, one of our colleagues at MIT, John Oxendorf, is a structural engineer and archaeologist, right? He loves to sort of look at old structures, including Inca sort of architecture, but also Gothic and Spanish vaulting systems. So John was a collaborator and colleague. He was also one of the structural engineers. We had 4 different structural engineers. So surely we've built lots of arches before, and that gives us confidence that it works in theory, but no one's done it in a long time. And so the contractor immediately said, I'm going to post-tension this. I'm going to put some tension wires in there. We're going to tighten it all up, and it's not going to go anywhere. John was convinced that we could just have it, use gravity and geometry, to shed thrust, from the keystone out. I think probably, Gothic architecture would have used smaller blocks, just in terms of handling and sort of managing. So we sort of went for a kind of supersized block. In a way, we had 32 blocks, probably around 30 joints, and so the less joints you have, the less sort of, insistence on precision, because every joint is a moment of potential failure. If 2 joints don't align, they could open up. And so we used incredibly large blocks. The largest blocks we could get our hands on, the largest blocks we could get on a truck, and the largest blocks we could conceivably fabricate. And so our technology for fabricating and lifting and placing blocks was probably, certainly more advanced than what the Gothic masons were doing, not to take anything away from them. But I think it was interesting to work in a mode that was archaic and state of the art, simultaneously. And I think that's where the great sort of eureka moments were sort of working with modes that had no tension. The software couldn't calculate because it didn't have tension in it. Most structural software relies on tension and compression. If there's no tension, then the software didn't know what to make of it. So it was perplexing.
We'll see if Laure can get in and ask you the next question. If not, I have one also. So
Yes, I had a question for Eric. I found your monument at UVA, truly fascinating. You mentioned at first a historical reality that enslaved laborers worked or were confined to a kind of underground space, right? If I understand correctly. Yet your monument is, really in open air, totally open onto the landscape. I was wondering if you try to incorporate that idea of, um, underground, kind of darkness or shadow, or if you deliberately decided to perhaps not incorporate that into your monument.
Yeah, no, I started with the pavilions because they're so fascinating, because it shows Jefferson's hand and skill as an architect, not just an architect, but a land surveyor, a kind of a site works engineer, that was kind of masterful in his sort of deception, using architecture to sort of obscure the sort of the reality of his utopia. I think the monument, we call it a memorial. The memorial is sort of embedded in the ground, and we really wanted it to be a kind of clearing, almost like a clearing in the woods. I think it doesn't take much to sort of find a place for people to gather. And so we wanted the architecture to kind of recede and sort of just create a kind of simple bowl-like figure. Turns out the figure was the exact same size as the dome. We didn't start that way, but it sort of created this sort of dialogue with the dome. And maybe the dome is also sized as a kind of optimal sort of size for span, but also for gathering. What's the size of an intimate gathering? So that was kind of almost accidental, that sort of relationship. But our intent was really just to create a hollow, a kind of void where people could fill it. And so rather than a monument which occupies space, it's really a kind of hollowing that is then filled by people.
Thank you.
So I have an observation, or at least a theory about your work, which fascinates me, and that is that it seems that there's always reliance upon technology, scientific research, and then there's also this empirical. It's almost as if everything then gets suspended and tested and verified, and there's this moment where the work really kind of confronts its premises, which I find fascinating. That is perhaps for a longer discussion, and somebody has asked you a very, I guess, long question, but I'm still going to read it to you, and if you can answer it very quickly for us, or at least think about it, is Eric, in your opinion, what's the most important feature of tectonics? Which is a very difficult question to answer, so here we go.
I was struck by Alejandro's sort of assertion that sort of tectonics a la Ken Frampton are kind of on their way out. I'm still sort of processing that. I mean, I think we also grew up with that book. That was the book that told us that there was a right way and a wrong way to detail, and the tectonics is an articulation of that sort of appropriateness. And so I don't believe we're being appropriate. I think we're always being speculative. So in that sense, I disagree with Frampton's, like there's one way to do it and there's a right way to do it. I feel like materials are asking for misuse at all times. And I think with new technologies, we're finding ways to sort of stretch their capabilities. So in that sense, I am also interested to talk with Alejandro about, post-tectonics, and material misuse. How might new details emerge with new technologies? But I tried to show, I think in the talk, a kind of skepticism for the kind of technical kind of expressionism. So we're not interested in sort of a kind of virtuoso kind of expression of technology. I think we're trying to achieve very simple goals, a kind of hollow, an arch, a kind of span, and the technical comes in to help us achieve those stated desires, so I think we're not sort of, I hope we're not being kind of uncritically kind of celebratory of technology. I think we're being very self-consciously sort of users of technology and very much aware of the kind of discourses that surround those acts of precision or imprecision. So maybe that helps.
Great, thank you so much, Eric.